Okay, this video is about relative atomic mass. That means like when you're looking at the periodic table and you see, a symbol for an atom written like that. Let's say calcium. Calcium's element number 20, and it has 20 protons. But then you see down here, there's some other like number written here that's usually not a whole number. So this is what we call the relative atomic mass. We're going to break this down and have a look at the isotopes that contribute to that number. So first, maybe it's helpful to review a little bit about what we see displayed on the periodic table and what it all means. Okay, remember that for the various elements, we have the symbol, that's like the short form code, letters that represent that element. In this case, it's calcium. And then we have the atomic number. That's going to be the smallest number that's displayed. The atomic number, remember, is the number of protons. And remember that this is the identity of that element. So in other words, to have 20 protons means you are calcium, okay? If you change it to 21 protons, it's not calcium anymore, it's scandium, Sc. And if you change it to 19 protons, it's not calcium anymore, it's potassium, okay? So the nature of what it means to be calcium is it means like an atom that has 20 protons in it. Then we see this other number down here. This is what's referred to generally as the mass number, but when it's a decimal like this, like it's presented on the periodic table, it's generally referred to as the relative atomic mass. And what's kind of funny about that is this is an average mass, okay, based on the fact that like we know what contributes to the mass of an atom are the protons. They're heavy and they have a general mass of 1. And neutrons, they're heavy and they have a general mass of 1. So this is like the protons plus neutrons if it's the classic mass number. But in the case of what's actually displayed there, it's an average of all of the naturally occurring isotopes of that element. So what does that mean? It means like naturally there's some calcium 40, but there must also be some calcium 41 that contributes to some of that mass. That's why we see the relative atomic mass or the average atomic mass being 40.1. That's to show you that in a natural sample of calcium that we find on Earth, there is still some of this. Okay, there's some calcium 41 that's contributing to the mass. It's mostly this, right? Mostly calcium 40. That's why that number is closer to 40 than it is to 41. So we're going to break down how we know that and how we can use the output from this technical device in chemistry and physics called a mass spectrometer to figure out what are the naturally occurring isotopes of these elements. And then how can we actually determine what the relative atomic mass, the average atomic mass, is for each particular element. Remember that isotopes as displayed right here, okay, calcium 40 and calcium 41. Remember, those are different forms of the atom with the same number of protons but a different number of neutrons. And so each of those respective atoms would have its own little symbol. You know, we could say like, all right, well, we could make a calcium 40 like this, and we could represent a calcium 41 like this, right? And so we're saying that there's a combination of both of those that contribute to reality. When we dig up some calcium or we refine some calcium on Earth, what do we find? We find a mix of these two different isotopes. All right, so let's say we are looking at the output from a mass spectrometer, and we call that a mass spectrum. So it might look something like this over here, this little graph I've produced. That would be what you see on the computer hooked up to a mass spectrometer. And we'd see the two peaks. Okay, this peak represents how much boron 10 there is. You know, you see the total mass is 10. The mass would be in atomic mass units, which you can use basically AMU for it, or you can use U like I've done over here. Okay, and then there's the peak that represents the boron 11, and you can see that corresponds to around 80%, but I've got the precise value over here, and this corresponds to around 20%, but we've got the precise value here. So if we know the sample of boron, imagine we could see this with more precision. The sample of boron is 19.91% boron 10 and 80.09% boron 11. Obviously, those add to 100%, which is good. That accounts for all the atoms in the sample of boron that we put through the mass spec. Then the question is, and there's no question actually written here, but what is the relative atomic mass of boron? What's the relative atomic mass of boron? So see if you can use those precise values there on the table right there, and you could actually determine the relative atomic mass of boron. Okay, what do we have to do to determine this? Well, we have to do something that's technically referred to as a weighted average calculation. Okay, so you're going to take the percentage of each isotope as a percentage. So 19.91% is 0.1991. And you're going to multiply that by the mass of that isotope. Now, the simple thing to use for mass would be 10. But you can see here that we've got even more precise masses than that. And now you might be asking yourself, why on earth would the mass of a boron-10 atom not be 10? It has, 10, whatever they call them, 10 particles, heavy particles in the nucleus. They're actually called nucleons, protons and neutrons. So why would it not be 10? Well, because you may recall that at some point you learned a proton is close to 1. Okay, it's almost got a mass of 1, and a neutron almost has a mass of 1, but not exactly, and I don't even remember what it is. It's something like a neutron has a mass of 0.0019 or something, and a proton, they're not quite exactly one atomic mass unit. You might say, well, why not? Isn't that how we define the atomic mass unit? The atomic mass unit is actually defined relative to the mass of a carbon-12 atom, which is arbitrarily assigned a mass of 12. So the whole thing is this relative system, and then with more precise measurement, we find out that the proton and neutron are not exactly one. So anyways, we can present these masses even more precise than just saying they're 10 and 11. So if we're presented with them, let's use them. Okay, so back to our weighted average calculation. So our weighted average calculation is going to yield for us, let me just write it here, this is doing weighted average, 19.91 times the mass 10.01293, that big ugly number. Then we're going to add to that the proportion that's boron 11, which is most of it. That's the 80.09% written as a decimal like that, written as a percent. And then the proper mass of that, which is that ugly thing up there. Okay? All right. So then if we do this, we should get the proper relative atomic mass of boron. Okay, punch that all into my miraculator. And don't mess up the brackets when you're inputting that. You might have to pay attention. Pay attention to this part all being in a bracket and things when you put it in. Anyways, it spits out the weighted average of about, and I'm going to round this a little bit, of about 10.81 AMU. Okay, I'm rounding it to 4 sig figs because these percentages initially were only given in 4, so I think I'll stop there. Okay, so what's that tell you? That tells you if we're actually properly looking at the element boron on the periodic table. Okay, symbol B, it's element number 5. Right, just checking my table. Yes, it is. That means it has 5 protons. And then we would display its relative atomic mass as 10.81, representing the proportion of it that's boron 10 and boron 11. Okay, let's look at another example where we have to use a different method and look for something else. So if we're given that an element like gallium, in this particular case, okay, has a relative atomic mass of 69.723 AMU, atomic mass units. If it's known to have only 2 naturally occurring isotopes, and here are those naturally occurring isotopes, gallium-69 and gallium-71, determine the percent abundance of each isotope. Okay, so what you have to do in this case is you have to do the same weighted average calculation, but we're going to have to use a little bit of algebra to determine the respective percent abundances of each isotope. So what you do is you say, let's let X be, let's say that's going to be the gallium-69 abundance. Okay. So if we do that, then we can build an expression where whatever the abundance is of gallium-69, we're going to put its actual mass next to it, which is 68.9257. Okay, we're going to add the abundance of gallium-71 to that. So the thing is that as a percentage, okay, and if we look at those percentages like we did expressed as decimals, what the value then, the remaining isotope after X is allotted to the 68.9, the gallium-69, the remaining is going to be 1 minus X, okay, because really X plus 1 has to equal the whole thing, right? It has to be one whole 100%, right? So we would have then 1 minus X times the mass of the other one, 70.9249, okay? And then that whole thing is going to equal the relative atomic mass that was given, 69.723. So this is what we're going to have to solve. So a little bit of algebra is required here. So if we then, distribute the X through there, we're going to have 68.9257X plus, don't forget you have to do the whole distributive property thing and put the 1 through, so that's going to be 70.9249 minus 70.9249x equals 69.723. Okay, 723. Can you see that or not? Let me fix that number up a little bit. Here. There we go. Okay, then you group your like terms together. So let's do the x's on the left here. If you do the 68.9257x minus 70.9249x, that is going to give you negative 1.9992x. I did that on my calculator. And then if we subtract the non-x terms from each side, so we subtract the 70.9249 from each side, that is going to give us, we're doing this, if I can write that in there. Sorry, it's going to get a little messy, but we're going to take that out of there, and we're going to do it over here. And again, consulting my local miraculator, it says that's negative 1.2019. Okay, and then so we'll divide both sides by the negative 1.9992. Of course, that negative should drop out because that's going to be a nasty thing to have there. We can't have a negative abundance or anything. And that gives us x equals 0.601. Close enough. I'll just round it to 3 in this case. Which means what? Go back and say, what did X mean initially? Well, we said that X was going to be the gallium-69 abundance. So therefore, the gallium-69 is 60.1% abundance of all the naturally occurring isotopes of gallium. And the rest of it, gallium-71, is going to be, the 1 minus X. So what's that? 39.9%. It's got to add to 100 abundance. Okay, hopefully that makes sense to you. You could double check your work just to see, like, does this jive with reality? We see that it has a relative atomic mass. If you look at what the actual given was, it's closer to 69 than it is to 71, and that's what we would expect if there's a greater abundance of 69 than there is 71, right?